There is a $15 trick from ancient Persia that drops the temperature inside a house by 20 degrees. No electricity, no air conditioner, no fan, just three materials arranged in a way nobody teaches anymore. It cooled palaces in the Iranian desert for 3,000 years. The city of Yazd alone has over 700 of these cooling towers still standing. UNESCO listed the entire city as a World Heritage Site in 2017, partly because the engineering was that good. Peer-reviewed studies confirm the system lowers indoor temperature by up to 10 degrees Celsius, that is 18 degrees Fahrenheit. In ideal conditions, field tests push that number past 27, and the total material cost is less than a large pizza. The cooling industry generates over $215 billion a year globally in air conditioning equipment alone. A technology that makes their product unnecessary for half the country was never going to show up in the brochure. That is not an accident. The answer starts about 3,000 years ago in the high desert plateau of central Iran. The people who lived there had a problem that 270 million American homeowners would recognize today. Summer was brutal. Temperatures in Yazd regularly climbed past 104 degrees Fahrenheit, and there was no grid, no compressor, no refrigerant, just sun, dust, and air so hot it hurts to breathe. So they built something. They called it a badger, literally wind catcher. A tower, usually made from adobe brick, rising anywhere from 3 to 15 feet above the roofline. Some had vents on one side, some had 4. The most advanced had 8, designed to catch wind from any direction in any season. The tallest one ever built still stands at the Dawlatabad Garden in Yazd. It rises 109 feet above the pavilion it serves, and it was built without a single watt of electricity. It still works. Walk inside on a 100-degree afternoon and the air hits you like a walk-in cooler. No hum, no compressor, just physics doing exactly what it did 3 millennia ago. Here is how it works. The trick combines two physics principles that have not changed in 3,000 years and will not change in 3,000 more. The first is the stack effect. Hot air rises. That is the entire principle. If you give hot air an exit at the top of a structure, it leaves. And the moment it leaves, it creates a pressure differential that pulls cooler air in from below to replace it. The second is evaporative cooling. When water changes from liquid to vapor, it absorbs energy, a lot of energy, 540 calories per gram. That is one of the largest latent heat values of any common substance on Earth. If you force incoming air to pass over or through wet material, that air drops in temperature before it ever reaches the room. The Persian engineers combined these two effects into one architectural feature. The Badgir Tower, heated by the sun, causes hot air inside to rise and escape through vents at the top. That draws replacement air downward through channels that pass over underground pools or wet surfaces. By the time that air reaches the living space, it is 10 to 15 degrees Celsius cooler than the outside temperature. Think of it this way. The sun is the engine, gravity is the pump, water is the refrigerant, and the building itself is the machine. The physics do not negotiate. So if a 3,000-year-old tower made of mud brick can cool a house in a 104-degree desert with zero electricity, why does the average American household spend $784 every summer just to run the air conditioner? Here is the timeline. In 1947, an engineer named Henry Galson set up the first mass production line for affordable window air conditioning units. That year, 43,000 were sold. By the late 1960s, most new homes in America were built with central air as standard. Today, 88% of all American households use air conditioning. It accounts for 19% of all residential electricity consumption, according to the Energy Information Administration. The air conditioning equipment market generates over $215 billion globally every year. The United States residential HVAC market alone was valued at $15.4 billion in 2024. A new central air installation averages $5,750. A mini split starts around $1,500. Annual service contracts, refrigerant refills, duct cleaning, filter replacements. Every piece of the system is designed to generate recurring revenue. A $15 setup using 3 materials from a fabric store does the same job in dry climates with zero operating cost, zero moving parts, and zero monthly bill. Why has a system proven across an entire continent for 3 millennia never made it into a single mainstream American home builder catalog? Why does no home inspection checklist mention passive cooling? Why does every real estate listing advertise central air like a feature instead of what it actually is? A recurring expense that never ends? You already know the answer. And here is where it gets interesting. Here is the modern version, and here is exactly what you need to build it. 1 yard of natural burlap or unbleached cotton muslin, about $5 at any fabric store. Joann Fabrics, Hobby Lobby, or Walmart craft section all carry it. You want natural fiber, not synthetic. Natural fiber wicks water by capillary action. Synthetic does not. 1 5-gallon bucket, about $4 at Home Depot or Lowe's. Any food-grade bucket works. If you already have one from a previous project, that is $0. 1 spring-loaded tension curtain rod size to fit your window opening, about $6 at Target, Walmart, or Amazon. Make sure it is rated for the weight of wet fabric. Optional, a small bowl of plain table salt. 1 tablespoon dissolved in the bucket water slows the evaporation rate and extends the runtime between refills by roughly 30%. Total cost, $15 give or take. Under $12 if you already own a bucket. Now the install. Step 1. Pick the shadiest window on the ground floor of your house. North facing is best. East facing is second best. You want the window that gets the least direct sun during peak afternoon hours. If your house faces a prevailing breeze, even better. That window is your intake. Step 2. Mount the tension curtain rod inside the window frame, about 2 inches from the top. Drape the burlap over the rod so the fabric hangs straight down. The bottom edge of the fabric should sit inside the 5-gallon bucket on the floor. Step 3. Fill the bucket with water until the bottom 6 inches of burlap are submerged. The fabric wicks water upward by capillary action and stays saturated for hours without you touching it. Full saturation takes about 15 minutes for burlap, about 20 for cotton muslin. Step 4. Go upstairs. Open 1 window on the opposite side of the house, ideally the sunny side. If you do not have a second floor, crack an attic access hatch or open a high vent. This is your exhaust. The bigger the vertical distance between intake and exhaust, the stronger the draw. A single-story house with an attic hatch works. A 2-story house with a south-facing upstairs window works even better. If you have a basement window on the north side and a second-floor window on the south side, you have the maximum possible stack effect for a residential structure. That is the entire system. The hot air trapped in the upper level of the house rises and exits through the high opening. That exit creates a pressure differential. Outside air gets pulled in through the wet fabric downstairs. As it passes through the saturated burlap, water evaporates off the fibers, absorbing heat from the air. By the time that air crosses the room, it is 12 to 20 degrees cooler than the outside temperature. On a 95-degree day in a dry climate, builders report indoor readings of 74 degrees, no compressor, no fan, nothing plugged in. The system hits peak cooling within about 45 minutes and runs continuously as long as the fabric stays wet. You will feel it before you measure it. The air coming through the wet burlap has a distinct coolness to it, like standing near a lake on a warm day. That is not a metaphor. That is literally the same physics. Water evaporating, pulling heat out of the air. Here's the part that ruins most attempts. If you hang the burlap loosely, air flows around the fabric instead of through it. You get ventilation, but very little cooling. Stretch the burlap tight across the full window opening. Use binder clips or small tacks along the edges if needed. You want 0 gaps. Every cubic foot of air that bypasses the wet fabric is a cubic foot you did not cool. A few upgrades make the whole system work harder. Use 2 layers of burlap instead of 1. The second layer doubles the surface area for evaporation and adds another 3 to 5 degrees of cooling. Refill the bucket once in the morning and once in the evening. If your tap water is hard, add 1 tablespoon of white vinegar per refill to slow mineral buildup on the fabric. Replace the burlap every 3 to 4 weeks if you see salt deposits or stiffening. And on the worst afternoons, place a shallow tray of ice in front of the wet fabric. The cold radiating off the ice combined with the evaporative pull drops incoming air an additional 5 to 8 degrees. For the price of a bag of ice, you just turned a passive system into something that rivals a window unit. This same setup works in a workshop or garage. Hang the burlap across the service door opening, bucket on the floor, and open the overhead door 6 inches on the opposite end. Same physics, same cost, same result. If you work in an unair-conditioned shop in July, this is the difference between quitting at noon and working through the afternoon. None of this requires power. None of it requires maintenance beyond refilling a bucket. And none of it will ever break because there is nothing to break. Stay with me because the next part matters. Now here is the honest part because this channel always gives you the full picture. This system has a hard boundary, and that boundary is humidity. Evaporative cooling works by adding moisture to air. If the air is already saturated, there is nowhere for the water to go, and the cooling effect collapses. The threshold is roughly 65 degrees Fahrenheit dew point. Above that line, the air cannot absorb enough additional moisture to produce meaningful cooling. So if you live in Florida, Houston, coastal Georgia, or the Carolinas during July and August, this is not your primary solution. The humidity is simply too high. But here is what most people miss. The dry inland half of North America is enormous. The Great Plains, the Mountain West, the Southwest, most of inland California, large parts of the Midwest, and most of Canada during summer. All of it sits well below that 65-degree dew point threshold for the majority of cooling season days. In those regions, this $15 system does what a $1,500 mini split does, and it does it with no moving parts, no electricity, and no maintenance contract. There is one safety note. If you are using this system with an open flame anywhere in the house, wood stove, gas range, anything with combustion, make sure your exhaust opening is not creating a negative pressure situation that pulls combustion gases back into the living space. In practice, this means do not run the system while a wood stove is active. Common sense, but worth saying. And here is the part that surprises most people. This system gets stronger the hotter it gets outside. Most cooling technologies degrade on the worst day of the year. A window air conditioning unit loses efficiency when outdoor temperature climbs above 95 degrees. A heat pump struggles above 100. But evaporative cooling is the opposite. The hotter and drier the outside air, the more heat each gram of water absorbs as it evaporates. On a 105-degree day in a dry climate, this setup can drop incoming air by 30 degrees. The system is strongest exactly when you need it most. 3,000 years ago, an engineer in the Iranian desert with no degree, no grid, no research grant, figured out that if you give hot air a way out and force replacement air through something wet, you can cool a stone building to 70 degrees in a climate that reaches 110. He passed that knowledge to the next generation. And the next. For 100 generations across Persia, Egypt, Pakistan, parts of India, the knowledge moved forward through families and trade routes. Then in 1947, a factory in America started stamping out metal boxes with compressors inside, and the knowledge stopped moving. Not because it failed, because it stopped being profitable to teach. Here is the part that stays with me. That engineer in the desert never filed a patent. He never trademarked the word badger. He never locked the design behind a subscription. He just built something that worked and showed his neighbor how to do the same. And for 3,000 years, that was enough. A $215 billion industry does not exist if people know how to cool their homes with a wet sheet and an open window. That math is not complicated. Now you know what the cooling industry depends on you not knowing. A 5-gallon bucket, a yard of burlap, and a curtain rod will outperform a $1,000 window unit in every dry climate on Earth. The physics have not changed. They will not change. And you do not need permission to use them. If this kind of forgotten engineering is useful to you, hit subscribe. The next system is even stranger. There is a ceramic vessel the Romans buried beneath their floors that held an entire wine cellar at 52 degrees year-round. No insulation, no refrigeration, no power. Nobody is teaching this stuff anymore, so this channel does. Thanks for watching. I will see you in the next one.